Chapter 5, Conversions within Measurement Systems. So some keywords we have are conversion factor. So that's going to be very important for converting. So in this chapter, we're converting within the same measurement system. So converting from household to household, metric to metric, apothecary to apothecary. So a conversion factor is a ratio equal to 1 that is used to change one unit to another without changing the value of the answer. Dimensional analysis, DA, this is a way of completing these problems that the book does go a little bit more in depth with these problems. We are going to solve all of the problems with ratio and proportion, a method used for single step conversions between units and for calculating medication doses and dosages. It involves solving for two equivalent fractions using cross multiplication and division. So this is going to be the way that we teach it at Ross. Some of my students who are recent grads from high school do know dimensional analysis. We do not teach it at Ross. But if you by any means can get the right answer by doing dimensional analysis or you feel more comfortable, you go right ahead. So I'm going to skip past the pretest. If you're feeling comfortable with the subject matter, you can go ahead and answer the questions to test your knowledge. If not, work your way through the chapter and return to them for some extra practice. Now that we are familiar with the standard units of measurement in the household, metric, and apothecary systems, we will focus on converting from one unit to another within each system. All conversions and most pharmaceutical calculations can be completed using one of two basic calculation methods: dimensional analysis or ratio and proportion. So how many inches are in 2 feet? That is fairly simple for people in the United States because it is used in everyday life. We know that 1 foot equals 12 inches, so 2 feet will equal 24 inches. This is actually an example of the ratio and proportion method of solving a conversion. So ratio and proportion, it's also known as cross multiply and divide. And by cross multiplying, I mean diagonally cross multiplying, which can confuse students. They'll try to go directly across. It's diagonally cross multiplying, which we'll see in just a second when we solve example 5.1, and we'll go through those steps.
All right, example 5.1. How many inches are in 2 feet? We know that there are 12 inches in 1 foot. So that's our conversion factor. So on our proportion, we know we need to have the same units directly across on the other side. So we have 2 feet, 2 foot. How many inches is that? So then we're going to cross multiply diagonally. So this becomes 1x, which is really just the same as x. And then 12 times 2. So I'm just simplifying my problem down here. 12 times 2 is 24. So x equals 24. We don't have to do anything else because x is already alone. So our answer is 24 inches. How many tablespoons are equivalent to 7 teaspoons? Once you know all of the basic equivalencies from chapter 4, this becomes much easier. So we'll have a little sheet for you too as well. We can see from table 4.3 that 3 teaspoons is equal to 1 tablespoon, therefore. So that's our conversion factor. 3 teaspoons is equal to 1 tablespoon. And we could write this however we wanted. If we wanted to put tablespoon on top and teaspoon on the bottom, that wouldn't matter. We just have to make sure our units are the exact same directly across. And we want to know how many tablespoons. So x tablespoons are equivalent to 7 teaspoons. So we would do 3x is equal to 7 times 1, which we already know is 7. I'm going to just rewrite it as 3x equals 7. Now we want to get x alone, so we got to get rid of that 3. To do so, we're going to divide by 3, which gives us x on this side. And then we also have to do the same thing over here. So 7 divided by 3 is 2.33. However, we're working with a household system, so we actually can't make that a decimal. We need to leave it as a fraction, but we cannot leave it this way. So what we need to do first is do 3 into 7. So how many times does it go in there evenly? Well, 3 times 2 is 6, and 3 times 3 is 9, so it's going to be 2. So 3 times 2 is 6. We have 1 left. So that becomes our numerator, and our denominator becomes the 3 over there. So our answer is 2 and 1/3. Now, for example, 5.3 and 5.4. This is doing the exact same problems as 5.1 and 5.2, but it's using dimensional analysis, which we're not going to go through. Example 5.5, 24 tablespoons is equivalent to how many cups? So this is in the book, they're showing using dimensional analysis, but we are going to just use proportions. So we need to find a proportion between tablespoons to cups, but there isn't one. I mean, there is technically, but we don't have one on our sheet and there's not one in that table. So we have to do 2 different ones. First, we're going to use the 2 tablespoon equals 1 ounce. We're going to convert it to ounces, and then we're going to convert the ounces to cups. So we said 2 tablespoons is equal to 1 ounce. And we have 24 tablespoons. So how many ounces is that? And we'll do 2x equals 24 times 1, which is just 24. So we have 2x equals 24. We want to get rid of the 2. So x is alone on this side. That's what we're solving for. And then we also have to do the same thing to the other side. So 24 divided by 2 is 12. So it's 12 ounces. So now we want to use our conversion factor between ounces and cups. So 8 ounces equals 1 cup. And we have 12 ounces. How many cups? So we could do, so 12 divided by 8 is 1.5. So we can do the long division and do 8 into 12, but hopefully you guys know that 1.5 or 1.5 is just 1.5.
Okay, so table 5.1 shows household equivalencies and conversions. So this is a nice little chart. We have the measurement, the abbreviation, and the equivalent. We also have the dry weight measurements. So just a little note, this book is saying that ratio and proportion is only appropriate with single step conversions, which is true. We just might use several single step conversions instead of placing them all together like DA does, and it's really hard with the units sometimes. I'm going to skip over practice problems A. Because the metric system is based on units of 10, conversions can be made within the system by moving decimal places. This is a quick method, but a thorough understanding of the relationship between units is needed to master it. So just like the other problems, I recommend using ratio and proportion to solve these and not moving decimal places. If you feel comfortable doing that, then by all means, go ahead. If you get the right answers, great. I just know a lot of students, when they use the moving decimal places, get the wrong answer sometimes. The units used for weight in pharmacy are from largest to smallest, kilogram, gram, milligram, and microgram, with a 1,000-fold or 3 decimal place factor difference between each closest measurement. You can see that here. The units used for volume in pharmacy from largest to smallest, liter and milliliter, with a 1,000-fold or 3 decimal place difference between each of those. The only conversion factor that is used in pharmacy for volume is 1 liter equals 1,000 milliliters. And that is something that you're going to want to make a nice comfy spot in your brain for, because you're going to need to know that by heart. Table 5.2 shows metric conversions used in pharmacy for weight and volume. Just a little tech note, when numbers are in an answer are 1,000 or more, make sure you add commas to avoid mistakes. So converting from larger metric numbers to smaller metric numbers, the placement of the decimal point is based on moving through powers of 10 by moving the decimal point. First, determine the number of the decimal place difference between the two numbers. When converting from a larger metric unit to a smaller one, move the decimal point to the right by the number of the decimal place between the two, or multiply by 1 plus the number of zeros in the equivalent. This method can be verified or checked by using ratio and proportion, or DA, as well. The following examples depict moving the decimal point, multiplying by 1 plus the number of zeros difference, ratio and proportion, and DA.
So example 5.6, they have us moving from the metric system to the metric system. So technically you can use place values like they do down here and get the answer. The only thing is with doing it this way, I find that most students get the answers wrong. So I think it's a lot easier to do a ratio and proportion. So we're using the 1 liter equals 1,000 milliliters. So let's do that now. So we have 1 liter is equal to 1,000 milliliters. And we have 1.2 liters. How many milliliters is that? So we have 1x, which is just x, is equal to 1.2 times 1,000. So we'll get out our calculator and just do 1.2 times 1,000. So that is going to be 1,200. So if 1 is 1,000, then it makes sense that 1.2 is 1,200. All right, so example 5.7 is the same, trying to move it from the decimal points, but we're just going to do proportions. So we have 5.4 kilograms, and we need to change that to milligrams. So looking at our conversion sheet, we don't have a direct conversion between kilograms to milligrams. So first we're going to have to convert it to grams and then convert grams to milligrams. So we'll have to do 2 proportions, which I still think is easier than matching everything up for dimensional analysis. So 1 kilogram is equal to 1,000 grams. And then we're going to use 1 gram equals 1,000 milligrams. So 1 kilogram equals 1,000 grams. And we have 5.4 kilograms. How many grams is that? So this 1x becomes just x is equal to 1,000 times 5.4. So 1,000 times 5.4 equals 5,400 grams. Now we have to convert those 5,400 grams to milligrams. So we'll just place our grams up here. How many milligrams is that? So this again will become 1x, which is just x, equals 5,400 times 1,000. So x is equal to 5,400 times 1,000, which is 5,400,000 milligrams.
Converting from a smaller metric number to a larger metric number. First, we're going to determine the number of the decimal place difference between the two numbers. When converting from a smaller metric unit to a larger one, move the decimal point to the left by the number of the decimal place difference between the two, or divide by 1 plus the number of zeros and the equivalent. So small unit to large unit, and then divide. We'll do example 5.8 that way.
Example 5.8. So we're moving from milligrams to grams. So we should already by now know that 1 gram equals 1,000 milligrams. We'll place our 5 milligrams down here. How many grams? So we have 1,000x is equal to 1 times 5, which is 5. And then we'll divide the side by 1,000 to get rid of that. We also have to do it to this side. So 5 divided by 1,000 is going to be 0.005. Remember, we always have to have that leading zero before the decimal. So example 5.9, we already used this conversion factor of 1 kilogram is equal to 1,000 grams. And we want to go from grams to kilograms, so I'm gonna use this for one side of the proportion. And we have 500 grams. How many kilograms is that? So we have 1,000x is equal to 1 times 500, which is just 500. And we want to get x alone, so we got to get rid of that 1,000. We now have x alone on this side, but we have to divide that side by 1,000 as well. So 500 divided by 1,000 is going to give us 0.5 kilograms.
The apothecary system of measurement. So the measurement of grains is still found on labels of nitroglycerin, codeine, phenobarbital, aspirin, and ferrous sulfate, which is iron. Some physicians will order these medications as well as acetaminophen in grains, which is the apothecary unit used most in pharmacy. Apothecary symbols are found on the ISMP list of error-prone abbreviations, symbols, and dose designations. They will be used in chapters 5 and 6 only. Apothecary equivalents that will be used as conversion factors in practice, problem C, are found in table 5.3. So we have a nice little chart here from apothecary system symbols and equivalencies. So we have the fluid dram, the fluid ounce, so those have the FL in front of them. And if you recall, this is a 3, this is like a 3. But that actually stands for dram, and then the ounce is like that 3 symbol with a like little Z on top. All right, so we'll go ahead and do example 5.10.
All right, so if we look at our conversion sheet, we can see that 1 fluid ounce is equal to 1 fluid dram. So I'm going to put 1 ounce equals 1 fluid ounce equals 8 drams. So I'll put that on one side of a proportion. And we have 2 ounces. How many drams is that? So this 1 times x just becomes x. So 1x is just x. And then 8 times 2. So x is equal to 8 times 2 is 16. So that's 16 fluid drams. And we would need to do FL, so our symbol. And then we would need to do 16 in Roman numerals. Which let's Google it. See how bad I am at Roman numerals. So XVI. This would be our answer.
Three measurement systems are used in practicing pharmacology. The household system is used most commonly on a daily basis in the United States and is also used for administration of liquid medications at home if the appropriate dispenser is not provided. However, using the household system for volume provides only approximate measurements because of the difference in utensils. It may cause an inaccurate dose when used for administering medication. The metric system is used as a standard unit of measure throughout the world and is instructed on multiples of 10. Most medications are designated in the metric system. The final system, rarely used today, but still found with some medications, is the apothecary system. Although the system is not popular and its use is being discouraged, these measurements are still seen occasionally with some medications.